Here we go. 12.1 Introduction to Limits. So what should we learn today? We're going to understand the limit concept, use the definition of a limit to estimate limits, and determine whether the limits of functions exist. Use properties of limits and direct substitution to evaluate. So the limit concept and definition of limit. Starting off, this is the definition of a limit. So on your space, you don't have a whole lot of room to write the definition. The main thing is we want to make sure you write this. The limit as x goes to c, f of x equals L. Okay, that's the main thing I want you to write. Okay, and what this means is this: if f of x becomes arbitrarily close to a unique number L as it approaches c from either side, then the limit of f of x as x approaches c is L. That's it, basically. So basically it's just saying as you approach, whatever value you're approaching is your limit, your L. That's why what's mostly important is what's in the little red box. Okay, so I kind of made last period write down everything. Just write with the red box. All right.
You like us more than that's what I
I become more prepared for your class period.
That's what happens. Gotcha.
That's what happens. All right. Okay, so we wrote down what's in the red box.
Yeah.
All right, moving on. So now it says estimating a limit numerically. So when we're talking about a limit numerically, we want to look at not what the value equals. Does that make sense? You want to know what is it approaching. Okay, so notice here how we have this function x squared plus 4x plus 4 over x plus 2. Why, when I graph it, does it turn into a line? Yes. It divides evenly. It has a hole in the function. Does that make sense? It's removable discontinuity. Remember those words? Removable discontinuity. If I was to factor out x squared, it becomes x plus 2 times x plus 2, and it's all over x plus 2, right? So then all I'm left with is what? X plus 2, and x plus 2 makes a what? A line, right? X plus 2 makes a line. So what ends up happening is that technically at -2, there is a hole. It's just, we can't see it. So we've noticed how I can't see it on the graph, but when I go look at the table, what do you see? An error, right? That error means that there's a hole. Okay, this represents there's no value. So there's no value, but that doesn't mean there's not a limit, because your limit and your value do not have to be the same. Okay, so again, the error here represents that there is no value, but is it asking us for the value? No, it's asking us for the limit as it goes to -2. Okay, so when we're looking at the limit, we're analyzing what would it be if it was approaching here? It would be 0. So the limit as x goes to -2 for x squared plus 4x plus 4 all over x plus 2 would equal 0. Does that make sense? Because that's where we'd be going, but because there's a hole, it doesn't have a value there. Yeah? So there's a difference between the limit and the value. The limit is saying, if I could go, where would I go? The value is saying, if I'm there, what do I equal? Okay, and I don't equal anything. It would equal 0 if it didn't have that. Exactly. The closer and closer from left to right I get to -2, I'm getting closer and closer to 0, but will I actually ever equal it? No, I'm approaching 0 though.
So limit is just
What are you approaching?
without touching.
No, you could touch it eventually, but what you are just asking, what are you approaching?
Can you only see? What if you just calculate?
No, you
Like,
could do
what
it
are
by
you
hand.
approaching on the X or Y?
Like we could have did this without the calculator. We found that there's a hole, so there's no value, but then we could plug in -2 and find that we're approaching what? 0, right? Because -2 plus 2 equals 0. So we could find it without the calculator.
How do you find the what? No value there?
Because I have a removable discontinuity. This is what makes it no value, the removable.
If you plugged in like, so -1.99999, it would be really close to 0.
It'll be really close to 0. Yes.
Wait, so how is it?
I'm listening.
Oh, okay. Like, how is the limit approaching zero, is it like, is the limit always gonna be the x?
So-
the x-axis?
No, your limit's you're asking your function, where is it going? So if I'm heading from the left to -2, and I'm heading from the right to -2, where are they both heading towards? 0, right? That's your limit. What are they heading to? Where am I trying to go?
The limit is like x basically.
Yes, it's x could possibly equal that value, but it's not gonna necessarily equal it.
The value doesn't.
And the value in this case does not exist because I can't plug it in and it doesn't exist. All right, so here it is. The existence or non-existence of f of x when x equals c has no bearing on the existence of the limit. Okay, so whether there is a value or not, it has no bearing on whether there is a limit. So in this last example, we had no value, right? But we still had a limit. Yeah, got it? I 100% did that wrong in 6th period. I thought about it after. I was like, what did I just tell those people? And then fix my life. And they'll get this video and they'll hear me apologize. Sorry. Okay. Now, how do you know when the limit fails? How do you know when the limit does not exist? Okay, that's what we're trying to figure out. So a limit fails is when you say the limit does not exist. Okay. How does that happen? There's 3 ways. Way number 1 is that they're approaching different numbers. So if I'm coming from the left, but I'm heading to 5, and I'm coming from the right, and I'm heading to 6, is there a limit where I'm gonna meet each other? No, even if it's at a hole or an asymptote, we're still not meeting, right? Because of that. So therefore, the limit doesn't exist. Okay, the other one is that your function is increasing or decreasing without bounds. It's heading towards positive or negative infinity. Okay, it has no boundaries. The last one that we won't see very often is if it's oscillating. So if it's oscillating between 2 fixed points, that's the other reason why it does not exist. You'll see people write D, N, E, for the limit does not exist. Huh? Does not exist. D, N, E. Okay. So what's highlighted is what's important to write. If you're trying to figure out what should I write down.
It looks like there's not oscillate from the values that's like sign. Or can you do a limit on?
It's more of like a tangent where you have the asymptotes and you're going back and forth, like more like repeated asymptotes.
Oh.
Mhm. Sound effects and all. All right. So again, all your writing is to highlight it. If you didn't get a chance to write it, it is completely posted on your canvas. But for the sake of time, I'm going to keep going. Okay. So I'm going to show you an example of when the limit does not exist, and we're going to talk about why. So this is an example of where the limit does not exist. Okay. So the limit as x goes to 0, we have the absolute value of x divided by x, right? First off, we know the value doesn't exist, right? Why does the value not exist?
Oh, because you can't approach it from the left side.
No, the value. Why doesn't the value exist? So why can I let x be 0 in this problem? Like if it was just a regular function.
It would be.
Exactly. So we know that f of 0 is undefined, right?
Yeah.
And that's because it would be a 0 in the denominator. Okay. Now, yeah, you're adding it in at the top. It says write the example. Some. Does it not say it? Okay. Yeah, give an example.
You're right.
Okay, so here's our example. All right. So as the x goes to 0, absolute value of over x. Now, why the limit doesn't exist also? So yes, it's undefined, but the limit doesn't exist because let's look at the graph. If we were to graph this, notice how our graph is heading to 2 different points when it approaches 0, right? Coming from the left, it's heading to -1. Coming from the right, it's heading to +1. They are not approaching the same value as they head towards 0. Does that make sense? So this is why the limit does not exist. Yeah? Okay. Questions, comments, concerns? So this would be a D and E. The limit does not exist. Have y'all not ever seen Mean Girls?
I need a cigarette.
Nobody?
Yeah, give me one, too.
All right. Okay, so the picture's there to show you, but this is explain again. And so if I was doing it algebraically, I would be looking at, okay, coming from the right side, so as x gets bigger than 0, what is this gonna always equal? 1. Coming from the left side, this is gonna always equal -1, right? And so therefore, I know that algebraically, they will not ever approach at the same point. Unlike when we had our hole, at least it was both heading towards the hole. Does that make sense? This time, yes, we have 2 holes, but neither one are approaching at that hole, okay? And that's why it's D and E. All right, so just clarifying, f of x equals 1, f of x equals -1. This implies that the limit does not exist. Okay, because there's 2 set values at 0. Got it?
Yeah,
All right. Next, properties of limits and direct substitution. So properties of limits and direct substitution. You don't have to write this down. This is not in your notes, so we're just going to talk about it. Sometimes your f of x is going to equal your f of c. So just plugging in the value, right? That's what we mean by direct substitution. I can take the value of what my limit is approaching and just plug it into the function, okay? Now we're going to go over those times where this works, all right? When this works well, we like to call this a well-behaved function. It makes it easy for us to determine what the limit is, okay? So we call those well-behaved functions. Typically, it's a polynomial or a rational that doesn't have the denominator equal to 0. Those are our well-behaved functions.
it's like all of them.
Yes, because a linear is a polynomial, right? Yeah. All right, so these are our well-behaved situations. If we have a constant function, so we have a constant, if we have a linear, if we have a power, and if we have a simple radical. These are going to be our well-behaved functions.
Radical or just or no,
Square root,
all
cube
of
root, fourth root, fifth root, any root. Okay, so for example, I'm going to do an example of number 1. If I set the limit, Kevin, give me a number.
22.
22. As x goes to 22 of 5, what is it going to equal? It's just going to be 5. Because when your function is a constant, the limit is just going to be the constant because there's no change happening, right? I'm not going up, I'm not going down. It's no change. It's a constant situation. Does that make sense? Okay. So that's the one that people tend to get thrown off. Let's try the limit as x goes to 4 of x. Okay, this is just a linear equation. It's a linear equation with no type of discontinuity. It's just going through the origin. So if the limit as x goes to 4 at x, what's going to happen here? It's just going to be 4. It's a direct substitution. Your c equals your x. Got it? Do we see how that works for direct substitution? Yeah?
Yeah.
All right. Other examples that work with direct substitution. It's just saying that this also can be applied when you are adding, subtracting, multiplying, and dividing. Okay. So direct substitution still works if you have a linear function times a constant, which has a coefficient, right? So I can still do this if I had 2x, right? So for example, if f of x equals 2x, I can still find the limit with direct substitution. That's all it's saying. Does that make sense?
So why does it say BL? Where's that open?
Limit.
So
So this is called your limit. So the limit is the answer, the result.
as x approaches c.
So you would find f of x.
If c is multiplying like f of x,
Mhm.
x approaches c. then
Yes, exactly. So for example, if my f of x equals 2x, and I say, what's the limit as x goes to 2 of 2x. All you're gonna do is what? Plug in the 2, right? It's direct substitution. So what's 2 times 2? 4. So my limit's gonna equal 4. Conveniently, my limit and my value are the same. That's what happens with direct substitution. Your limit and your value are gonna be the same. Okay? All right, sum or difference. So if you're adding 2 functions, you would take the limit of each one and then add them together to get the limit of that function. Okay? If your product, if you have the product, you would take the limit of each one and then multiply their limits together. Okay, last, quotient dividing. If I have a function in the numerator, function in the denominator, I'm going to take the limit of the numerator and the limit of the denominator and divide them. And that's going to be the limit. Key thing here is that your k can't be what? 0. The limit of the denominator cannot be 0. Okay. And then last is your power. You're going to take the limit and whatever the power is, it applies to the limit. Okay.
Okay.
All right. So let's do an example. Here we have. So if we have the limit as x goes to 4 of 3x squared, what would that be? Is it not on your notes?
It's at the bottom.
Okay. I was like, did I skip it?
Oh, I didn't
What would it be?
What kind of?
The ones.
Okay, this is an example of direct substitution. So all I am doing is plugging that in. So we have 3 times 4 squared. That's going to give us 3 times 16, which equals 48. Doable? If it doesn't fit any of those categories that we just went through. So we went through the basic 4, right? Our constant. Yes. But thank you.
You can't remember if it's direct substitution. You just plug it in and get it fine.
Mhm.
How to do it.
Yep. You can test around. But that's as basic as direct substitution. So we have our rules to follow. We have our basic, our constant, linear, power, radical, parent, right? So if it's any of these, then we know it's going to be direct substitution. And then we have their modifications of them where we are multiplying, sum or difference, the product, the quotient, and then additional power. Yes? All right. So this is just reiterating limits of polynomial and rational functions. So when you are looking for the limit of a polynomial, it is going to always be direct substitution. Okay? If it's a polynomial, your answer is just going to be always direct substitution. Okay? If you have a rational, your answer is going to also always be direct substitution, but you need to be mindful of your denominator. You also want to make sure you factor before. Okay? How do we feel about our intro to limits? Doable? You're scared. Don't be scared. All right, so let's do another one. What do we have here?
But
We have a rational function. So does what we approach make our denominator equal to 0? No, it does not. So that means we can use direct substitution. So you get a 2, you get a 2. We have 4 minus 2 squared all over 2. And what do we end up with? 0. So our limit is 0. L equals 0.
Oh, you can put L.
And that's your limit. Yeah. No one's like, oh no, this is horrible. All right, I did have additional notes. That's why it says additional notes if you wanted to see more practice. So just really quick, we can go through it. Notice here how we had the parent quadratic, right? A quadratic is a polynomial. So therefore, direct substitution can be applied. Agreed? All right, next. Here we have a linear with a slope of 5. It's still a linear, so guess what? I can use direct substitution because of scalar property. It still can be applied. Yeah? Here, ooh, threw some trig at you. All right, here we have a trig and we have a quotient.
Whoa.
Ooh, fancy. Here we go. The limit as x goes to pi. Well, what is tan at pi? 0. Tan at pi is 0 because it's your y over your x. And at 0, that's 0 over 1, correct? So the tan at pi, the limit's approaching 0. The limit of x is just pi. And 0 over pi equals 0. Okay? So did it change? Any of these rules change just because I threw a trig problem at you? No, it did not. Okay? Here's another radical. Simple, straightforward. Radical is going to lead us to direct substitution. All right, another example with trig. Okay, and product. So this time you're going to take the limit of each factor. So I would take the limit of x and the limit of cosine x. Okay, the limit of x goes to pi. It's just going to be what? It's going to be pi. What about cosine? What is the cosine of pi?
It's negative one. I almost had it.
Okay. So we're going to end up with negative pi, right? So therefore our limit is negative pi. So these are your additional notes, just so that you can see how it plays out and how it works. Hopefully you can see that it's not that terrible with direct substitution. Too easy, right? All right. What about this guy? It's just got big for no reason, right? Do I really need to expand it? No, I can just go through and evaluate it, okay? But this is the justification why you can, because it's sum and power properties being applied, okay? And that concludes our introduction to limits. Yeah, so your assignment, I think I have the PDF of it somewhere. It's on there, but I was just going to show you. So on your assignment here, they just want to make sure you're okay with the table. So if you were to look at the table, what's happening, how is it approaching? But it's just evaluating. So if I have the limit as x goes to 3 of 5x plus 3, what's happening? Here you have a rational. Again, what's happening? Make sure with your rational that you do what first? Check if it can be factored and then evaluate your limit, okay? Here you have a graph to evaluate. Another graph, a sine graph. Ooh, what's going to happen there? And then you have an addition. So you have f of x and g of x. You are giving your limit, and then to find the limit of them combined, what do? Oh no. So yeah, you have 10 problems of just, nope, it's on your handy dandy canvas. It's already there. Yep. All right, that is it.